What specific problem does your proposed method aim to solve in the context of large language models? Please detail the challenges you identified in existing approaches to encoding and utilizing input embeddings.
Our proposed method aims to address the challenge of effectively encoding and utilizing the latent capacity of input embeddings in large language models, LLMs. Existing approaches often struggle with the quadratic computational cost of the self-attention mechanism, leading to inefficiencies when processing long contexts. While some methods have achieved significant lossy compression ratios, they still face limitations in lossless compression, typically capped at a factor of 10. Additionally, the operational space of embeddings is underutilized, as they primarily serve as single token representations rather than encoding multiple tokens or entire texts. By introducing trainable memory vectors, our method seeks to enhance the encoding capacity, allowing for the reconstruction of longer text sequences without loss of quality, thereby improving both efficiency and expressiveness in LLMs.
Can you explain how the proposed method of using trainable memory vectors works? Please illustrate the step-by-step process, including the theoretical principles and algorithmic steps involved.
The proposed method of using trainable memory vectors involves a systematic approach to compressing a sequence of tokens into a small set of vectors, referred to as mem vectors. The process begins by introducing a set of trainable vectors, denoted as m_1 l.dots m_k, which are prepended to the input token sequence, t_1 t_2 l.dots t_n. During training, the language model, with its parameters frozen, processes the combined input m_1 l.dots m_k t_1 t_2 l.dots t_i to predict the next token t_i+1, optimizing the mem vectors by minimizing the next token prediction cross-entropy loss. The theoretical underpinning of this method is grounded in information theory, where the capacity of the mem vectors is quantified in terms of the maximum number of tokens that can be reconstructed based on the information they encode. At inference, the learned mem vectors are used to initiate the generation process, allowing the model to decode the text based on the compressed representation. This approach effectively leverages the latent capacity of the input vectors to enhance the model's ability to handle long text sequences efficiently.
Could you walk us through a simple example that demonstrates how your algorithm compresses a sequence of tokens into memory vectors? Explain the main steps of the algorithm with this example.
To demonstrate how our algorithm compresses a sequence of tokens into memory vectors, consider a simple example where we have a token sequence consisting of the words, "The cat sat on the mat." First, we introduce a set of trainable memory vectors, denoted as mem equals m_1 m_2 l.dots m_k, which are prepended to the input sequence. In this case, let's say we use one memory vector, m_1. During training, the frozen language model processes the combined input m_1 t_1 t_2 l.dots t_n, where t_i are the tokens of the sequence to predict the next token t_i+1. The memory vector m_1 is optimized by minimizing the cross-entropy loss based on the model's predictions. This optimization allows m_1 to effectively encode the essential information of the entire sequence. At inference time, we start generation with the learned memory vector m_1 and let the language model decode the text, reconstructing the original sequence from the compressed representation. This process illustrates how our algorithm captures and compresses the information of the token sequence into a compact latent representation using trainable memory vectors.
What are the key theoretical and practical advantages of your method compared to existing alternatives in the field, particularly regarding compression ratios and information retention?
The key theoretical advantage of our method lies in its ability to achieve a compression rate of up to x1568 without any loss in reconstruction quality, significantly surpassing existing alternatives that typically achieve lower ratios, such as x480 with substantial quality degradation. Practically, our approach utilizes trainable memory vectors that effectively encode entire text sequences, allowing for the reconstruction of long texts with high accuracy, as demonstrated by LLAMA3. 128B, reconstructing up to 1568 tokens from a single vector. Additionally, our method establishes a direct connection between the latent capacity of input vectors and text cross-entropy, providing a quantitative measure of information retention that is not present in prior works. This connection enables us to isolate the contributions of the memory vectors to the model's performance, demonstrating that the compression ability is independent of the model's familiarity with specific texts. Overall, our findings indicate that the proposed method not only enhances compression efficiency, but also improves the model's capacity to retain and reconstruct information effectively.
Describe the experimental setup you used to validate the effectiveness of your method, including the datasets, benchmarking metrics, and performance measures that demonstrate its efficacy.
To validate the effectiveness of our method, we employed a systematic experimental setup using various language models, including Pythia, Opt, Olmo, and Llama models, with sizes ranging from 160M to 8B parameters. We utilized texts from the PG-19 dataset, which consists of books from Project Gutenberg, and fanfiction texts from the AO3 library, ensuring a mix of familiar and novel contexts for the models. The primary benchmarking metrics included decoding capacity in tokens, token gain, and information gain, which allowed us to quantify the number of tokens accurately reconstructed and the reduction in cross-entropy when using our trainable memory vectors. We evaluated the models across a range of text lengths, specifically measuring their performance at various thresholds of token-level accuracy, with a focus on achieving high accuracy is greater than or equal to 0.99 for effective compression. Our results demonstrated that models, like LLAMA3, 128B, could reconstruct sequences of up to 1568 tokens from a single input vector, showcasing the substantial capacity and efficiency of our approach in encoding and decoding long text sequences.
What significant results did you achieve while testing your proposed method, and how do these results compare with previous methods? Also, note any notable trends that emerged from your results, particularly regarding compression capacity and scaling with the number of memory vectors.
In our experiments, we achieved a remarkable compression rate of up to x 1568 with no loss in reconstruction quality, significantly surpassing previous methods that reported compression rates of x 480 with substantial quality degradation. Notably, LLAMA3, 128B, demonstrated the ability to accurately reconstruct texts of up to 1568 tokens from a single input vector, while smaller models with around 1B parameters achieved compression capacities ranging from 128 to 512 tokens. A key trend observed was the nearly linear scaling of compression capacity with the number of trainable memory vectors. For instance, Pythia 160M could decode texts up to 2016 tokens using 32 vectors, and LLAMA3, 2:1B, achieved perfect reconstruction for sequences as long as 7,168 tokens with just 16 vectors. Additionally, our findings indicated that the compression ability did not depend on the model's familiarity with specific texts, as larger models still exhibited substantial compressing power even with random texts. This suggests that the learned memory vectors provide a language-agnostic capacity for effective text generation and reconstruction.